Hi, everybody. You know, I haven't yet graduated to a C title. I'm not a CTO. So, not that it matters. But just wanted to set the record right, in case you're wondering why this says one thing or others would say something else. So, the general idea of my talk would be to first give you a sense of why we built what we built and what is it that we actually built in the last major release, because it was foundational changes that we did there. And finally, what are the things we're going to be building in the future? So you get a sense of Couchbase in the full umbrella of all the stuff that we're trying to do there. So there are three major trends that are reshaping the whole the database side of the world. First is hardware disruption. Their memory has gotten way cheaper, so all the assumptions that people made earlier about storing more data on disk is getting seriously questioned, because you can store more in memory and it's cheaper. Networks are getting way faster. 10 gig E is the standard now, 40 gig E is coming. It'll get faster and faster. There are InfiniBand networks which are now customized within the servers, but eventually those speeds will be available in LAN and eventually in WAN. All these are going to get faster. SSDs are disrupting storage. The spindle-based disk is about 1,000 times slower than this one. So it's a very famous statement by Jim Gray, is to say, flash is disk, disk is tape, flash is disk, and RAM locality of data is king. That's what he used to say. So the flash is now becoming the disk, and it is about 1,000 times faster than a spindle storage, which would actually be in seconds. This is milliseconds, and memory is in sort of microseconds. So each is 1,000 times faster. So the more stuff you store in memory, you're faster. Most of the time, CPU is sleeping. It's waiting for data to be fed. So the more closer you are to the CPU, the data, the faster your processing is. So that's the hardware side of the disruption. Then the application development has changed. Everything used to be server-centric in the past, not anymore. The model, view, and controller has gone through a dramatic shift where only the model is sitting on the server side, that is the data, and the business logic of manipulating that data. The other two stuff, the view and the controller, and the manipulation of data of what you're seeing, all that stuff is happening on the browser. All the Angular and Node.js stuff, the backbone, all the stuff is basically about getting data more on the browser and doing stuff asynchronously. So it's become stateless. Earlier, stuff used to be very stateful. Now it's stateless REST API serving you the data, and then you're doing rest of the manipulation and the magic in an asynchronous manner on the browser. And the same paradigm is now useful for building disconnected apps as in mobile. So it's more and more becoming like a disconnected application development. So that has changed. And one of the fundamental things that has changed out there is also people realizing the object relational impedance mismatch and how much it costs. At the end of the day, if you look at an application data, it's a JSON. It's basically a document format. The data is sitting in a document format. When you explode an object and just take the data portion of it, it's sitting in a sort of a more naturally a document format. Whereas because relational systems were so good, you went through a mapping of an object into a table and a column. You will do that ORM mapping. So entire industries have been built on this stuff, and I don't know how many countless amount of CPU and power and all were wasted doing this stuff, where you shred the document into tables and columns, deconstruct it and store it, and then you do the same magic reconstructing it so that you can at the end of the day show a document. I mean, most of the application, if you really look at it, it comes down to displaying documents. Most of the natural stuff that we always deal with are like documents. So that is another fundamental change that has happened. And a JSON We could have done the same thing using XML. Thank God we didn't do it, because XML had its own idiosyncrasies and formats and all that stuff, so you had to load a pretty heavyweight XML parser, and that took away all the advantages you had. So JSON, being so simple, sort of works. So being a JSON database reduces the impedance throughout the system. JSON is the object you're manipulating at the front end. JSON is what is transmitted on the wire, and JSON is what's stored in the database. So all the impedance is gone. It's faster, easier, simpler. Your life is easier, more efficient to code and get to the logic that you really want to build. The last is data. The data itself has changed. Earlier it used to be those lovely green terminals with just numbers and strings. Nowadays it's images and logs and tweets and every kind of unstructured data, including music samples or voice recordings. Everything can be sent as data across. So that's the size and shape, and the structure of data has completely changed. And if this is the reality of the world, then the databases that were built in the past do not take this into account. They are based on decisions that were made in the 80s and 90s, where disk itself was very expensive. And the data itself was very structured, as in you had to specify, even if you wanted to say, you want to store a string, you have to define it in your schema to say that it is char 256 or something like that. So, but these days you don't know what size of data you're going to get. Yes, in a tweet you can get 140 characters or something, but you can get a blog or you can get any other streaming data in there. So that has also changed the whole fundamental paradigm of what a database ought to be. So our response to this was how we wanted to basically build the Couchbase server, which I'll describe shortly. How this whole paradigm shift got us thinking, number one. The second portion of this whole thing is the fact that the whole data has a sort of a new continuous life cycle. The thing isn't rendering very well, but the whole idea I wanted to demarcate here was that the data life cycle goes something like this. You gather the data, which is what you store in a database. Then you query the data, which is the structured query languages help you sort of make sense of the data you've gathered. Then you search, which is the unstructured part of it. Then you sort of transport this data because you want to either have redundancy or you want high availability or disaster recovery. And into this we also add the synchronization portion of it, which is basically bring the data from the edge to the core, if you will. I'll get into that later. Then you report on this data. This is where you do sort of your advanced queries, where you can take a look at what type of data you have, what shape it has, and stuff like that. This is the gray area which starts now shifting from being an operational database. These are the typical things you do in a transaction processing or what is known as operational databases. From there, you now move on to the analytical side of it, where you're actually visualizing the data, analyzing the data. You want to recommend on this data, and finally predict. You want to build predictive models on it. And then this data becomes stale enough for you to retire the data. It's not as though this life cycle did not exist in the past, but it was in a very disjoint fashion. You would do maybe few phases in one system, and then you will take a huge dump of the stuff and put it somewhere else, and then you'll do some portion of the massaging and analyzing, and you will do some other disjoint stuff. Never did this whole life cycle complete itself. A classic example I can give you is that of Google. When you go to the Google search bar, I normally use the Starbucks example. Just if I'm sitting in the US and start typing STAR, pretty quickly the Google suggestion box comes up with a bunch of suggestions for Starbucks. And that's because Starbucks it's a coffee house, in case you all don't know. And that's the most popular search that people have done. So it's got that statistical analysis to say, if you had done STAR, The next character you're going to be looking for most probably is an R, and that's going to end with a Starbucks eventually. So that's the statistical analysis. That's the analyze part they've already done. Now that they go one step even further, that suggestion doesn't give me the Starbucks headquarters in Seattle. It gives me the nearest Starbucks right next to my home or wherever I'm sitting. It has also, on top of it, done a geospatial analysis and is able to recommend to me nearest Starbucks locations, because it's making a pretty good educated guess to say that you must be looking for a Starbucks to go get a coffee. Right, so what has happened is that the data is gathered, I'm searching for it, it has analyzed the data based on what is known as collaborative filtering is the field, where all of our searches actually goes in and there is a ranking system that you do, and then it's recommending based on that analysis, what is it that you really should be, what do you think you're doing? It's actually guessing your sentiment or what is it that you're going to be doing. And it's actually recommending what that you're actually looking for, and then you pick. That's how that whole autocomplete box is really working. It's a bag of tricks, but it comes to you very seamlessly. So this whole life cycle is happening in one shot, which wasn't happening before. Earlier, you would do this operational stuff in one system, give it to an entirely different IT department, and they will take a whole dump of it and do some analysis, and the report will come a month later. Now this is happening in nanoseconds, right? So we would eventually want to build a platform which allows you to do both the operational data store side and the analytical data side. This operational analytics is what we call it. We are not entering the Hadoop world. That can happen. That's a different data lake thing. We are not interested in that. So one is the disruptions. Other is this data lifecycle. Together, what we want to do, the response to this is sort of the Couchbase server that we built. The principles are like memory first, low latency, horizontal scaling were the main things we want to build this whole thing by. At the end of the day, I wanted to give a programming model which is flexible. So no schema. That was one of the main things out there. And all these document databases do not impose a predetermined schema in there, which allows you to build apps in an agile manner. So how do we achieve the memory first architecture is where we started with the memcached background. So it's a distributed cache with an integrated data store is how we achieve that memory first paradigm. So working set management with the fast storage, eventual persistence gives us that memory first characteristic. Combined with a pretty fast streaming protocol, which is in-memory protocol we have, because in a distributed system, one of the first and primary things we always have to do is move data around, both in terms of distributing the load evenly as well as for replication, cross data center replication, as well as intra-node replication for high availability and stuff like that. Then we are a shared nothing, no single point of failure architecture, which gives you a single node type, which means you can install the same thing in 50 different boxes. You don't have to do any specialization of one node is this, other node is that. All nodes are equal. At runtime, we elect a certain node to be the master. God forbid something happens to that and that went down, next one comes and says, oh, there is no master, I'll become the master. So this is the master election that we do at runtime. So the advantage of that is, since there is no single point of failure, if you chop off one head, another head comes up. And so, it takes care of itself. That's a big advantage. Many of the other ones have a specialized node, a router node, or this node or that node. If that goes down, you have to bring it up. In our case, it'll fix itself. The auto sharding, a smart way that we do it, it's like a consistent hashing modified, allows us to place data evenly across all these so there are no hotspots and stuff like that. Combined with the document programming model, it gives us the Couchbase server, the operational data store, which has the in-memory characteristics. So the way we have built this stuff is in such a fashion that as much as possible, we leverage memory and network, and as little as possible go to secondary storage, a disk or even SSD, because that's about an order of magnitude slower. that gives you the performance characteristics. We can do 5 million ops per second and stuff like that. So that's because of that. Let me briefly then talk about what we built in the last release to give you a more explicit sense of the features that is out here. This is a marketing slide, so at least gives you a high level of what we can boast about. But it finally comes down to two major innovations. One is called dynamically tunable memory, and the other one is called database change protocol. I will talk about them more in detail, the benefits of these things. And we also give you a little bit more sense of all the other features we built in this, as we claim 200 plus features that we put into this one. Typically, this is our standard product management sort of a feature list, if you will. We had fully integrated JSON programmability. Earlier you had to do some kludges. Now JSON objects are natively available for you to program in each of the programming models, programming languages we support. We have also done the first reactive capability in Java. So you can now sort of do your reactive programming. It sounds bad, but actually it is good. Reactive programming. The proactive stuff is old stuff now. You have to do reactive. We have a popular framework integration like Spring and for Node as well as for JavaScript and stuff like that. We also have our query language. There's a preview support for it. The tunable memory, I'll talk more in detail. Auto thread pool stuff, so things get faster replication using the database change protocol. We have improved durability. I won't go into details unless you know Couchbase server way in detail. It won't make sense to you. But the general feeling I want to just convey to you is that across the board we have sort of made changes which makes this more industrial strength. I mean, until now, many of the NoSQL solutions were not something that were getting deployed at production grade for mission critical scale, and that started to happen like Bob was describing the last year or so. So we have a lot more of these customers who are using this in mission critical applications at scale, which is deployed. And we wanted to build more features which allows these kind of larger deployments of hundreds of nodes in a cluster to be easily managed while still maintaining the performance at scale. With the dynamically tunable memory, what has really happened is that taking the Couchbase from being just a high performance database, which is what it is mostly famous for, into a high data density scenario as well, which means classic situation is that Couchbase server would be, most of the data is sitting in memory. The way I can put that more specifically is that every row of data, every key that you're maintaining in the database, and a certain amount of metadata that goes with that is always there in memory for your whole database. How many ever documents you have? Let's say you have 100 million documents, you need to have that ID and the metadata sitting in memory. Actually, the document itself or the value itself could be ejected, but the rest of the metadata had to be in memory, which is a pretty huge overhead. Because that's where we started, because we wanted to be memory first. But the more and more use cases we see, people have huge databases, terabytes of database, and they don't want to put terabytes of a good chunk of it in memory, because only a smaller subset will eventually get used. So the dynamically tunable memory gives you that ability to just, at runtime, tune the system, that bucket, to go from this high memory intensive, high performance scenario to this high data density scenario, so that you can eject the keys, so you can keep your memory consumption to be low. You can still have a terabyte of data on disk, but you could be surviving with maybe 100 megs in memory if you want. If that's your working set, if you can manage your working set efficiently, you'll be able to do this stuff. So a classic experiment we ran was 50 million documents, each with 2 or 3K to be the value of what we are storing in these documents. we saw that the metadata consumption came down from 3 gigs to 80 megs. A 10x principle that we normally use for innovation. If you can improve something 10x, don't bother. So with the larger scale, you will see this improvement to be even bigger. So this allows us to sort of play in a lot more use cases, which are traditional database use cases, where in traditional databases, you'll have a lot more sitting on disk and a lot less sitting on memory. So you can play there as well as high memory intensive scenarios like ad serving and other online retail sort of applications which want nanosecond responses. That's where we traditionally get deployed. From there, we can go to this side as well. So this is one of the dynamically tunable memory. And the whole idea here is that this is done at runtime with just a click of a button. You don't bring the server down. You don't have to redo something. You don't have to bring it back up in newer configurations, stuff like that. You just simply go to the admin consoles, set it to the high data density parameter, and all it takes is a few milliseconds. Depending upon the data, it could be a few seconds where the data set that's in memory is warmed up differently, and then you're ready to go. So that's a little bit of magic we pulled. People seem to enjoy doing this stuff, even just for fun. The other features worth calling out is that the major innovation was database change protocol. We built that protocol to address a variety of stuff, both in terms of performance as well as manageability. We want to build something which is performance by not involving disk. So it's a in-memory streaming protocol. It's got monotonically increasing sequence numbers, which gives us fine-grained control over how far back we want to go. We have snapshotability out there. We have failover logs. All those features enable us to do a lot of fine-grained control over how we want to manipulate data. It gives us a bunch of benefits. First is the rebalance gets faster because you have to move less data around, number one. Number two, the view consistency is fairly significant in our architecture, where views earlier used to be much slower because of being disk bound. And now the indexes get built, microseconds. Typically I say nanoseconds, but it gives us a 50x improvement in view consistency. What this allows you is to build applications which have, when you query for something, the consistency of what you're querying is near real time. In a distributed shared nothing architecture, that's fairly significant because you don't know the state of a shared system. In a shared nothing system, what is the latest consistency of the state of the whole cluster, 100-node cluster. But because of the in-memory replication, that capability that we have there, the indexes get built immediately, instantaneously almost, and that gives you a consistent state of the system. So you can now build traditional applications which give you those consistency guarantees. Replication durability is about when you want to write a piece of data, you can say that number one, replicate, number two, sort of store that in the replicated node as well. That is about 150 times faster. Our cross data center replication is 4 times faster because of the in-memory nature of the protocol. We build stuff like incremental backup and faster node recovery, which gives us the fine-grained control that we built into the protocol. So overall, in the last release, we moved the needle significantly in terms of performance, in terms of enterprise-grade capability. Just to give you a sense of it, the faster node recovery. Larger deployments, people are worried if a node goes out in a distributed system, we need to assume that there will be failures. If a node goes down, almost the whole cluster had to be disturbed because the data had to be redistributed, what was in that one node. With this delta node recovery kind of functionality, if a node goes out and then it comes back in, only the delta of the data that it actually lost is what it has to be it has to recover, as opposed to redistributing the whole cluster's worth of, let's say if you're storing a terabyte of data, earlier the whole terabyte had to be moved around. Now let's say only 100 transactions came in. By the time you went out and came back in, only those 100 had to be replayed. So that the protocol provides that capability for us to do this thing. So that's what we built in the last release, and we give you a very high level sense of what it is that we are building for the future. And before I get into this thing, let me sort of give you a sense of a couple of key principles on which we build our stuff. One is what we call as layer consolidation. We want to subsume a lot more layers into the data tier, so that way you actually benefit from it. A classic example is iPhone. People claim that it's 40 devices compressed into one. I mean, there's a famous ad that I saw in 1994, one of the famous American electronic stores called Radio Shack, a page full of ad of different devices. And all the functions of those devices, except perhaps for a huge subwoofer, you could do with an iPhone now. And the price of, if you had just included the price of each one of those that they were selling, were amounting to close to $6,000. And the iPhone is $600 in today's price, right? So a consolidation of layer gives you the benefit of things being faster, things being cheaper, things being more usable, because there is one consistent way to interact with them. You wouldn't have knobs for one thing, dials for the other, switches for the third thing, or some other controls. They all become one. Power unit is one. So like that, when you consolidate a bunch of layers, the efficiencies of scale improves the usability of such a gadget, dramatically. Something similar is what happens with Couchbase. We are at this point a cache and a database collapsed into one. So you're getting the performance of the cache and durability of a database. To that, we have added the sync gateway into that. So now at the data tier, we have subsumed something that application tiers earlier had to build, which is the sync capability. And sync of a multi-master data store is not an easy thing, and the conflict resolutions that goes with it, and the idea of what to synchronize in the multiple masters, who gets to see what, whole slew of issues that need to be solved in that. Now you have a place where that can be solved at a tier below. Earlier, even I have built systems like that, places like Siebel and others, where the whole sync was handled at the application tier, not at the data tier. So we're subsuming some of that, so it becomes easier. You heard earlier how some of the stuff is simpler. Of course, things have to get even more simpler as we keep innovating in that area. But the whole idea is we are sort of collapsing layers. I heard one complaint that we don't have search or geospatial index. Definitely, next thing to innovate on, next thing to add. Volker is sitting there smiling. He's my geospatial guy. So that's coming up in the next release, right? And for the search thing, we are working on some of that stuff. Text or keyword-based search is very important in the database system as well. All of them pretty much have something like that. But we will take it one level further as well, eventually, where earlier you can do, in the initial stages, you'll be able to do sort of a search, keyword-based search using structured query language. Eventually, it will become, it's another index at the end of the day. It's a reverse index. We already have secondary index coming up in the next release, so we'll have a reverse index as well. And so it'll collapse another tier. Perhaps, if we do it right, you wouldn't need a search system to be separately bought and integration and having data from here go there, crawled into the other. I built search systems as well. I was at BEA, and it's a nightmare because from the data, wherever different data repositories are there, you will have to write your own crawlers, which will then populate the search index, which is sitting separately, disjointly. And then whenever these crawlers run, the data is only as fresh as the crawlers, how often they run. And most of these crawlers don't run that often because they are intensive and all that stuff. So they'll run every other day, or sometimes they'll run it once a week and stuff like that. ITs get to make those calls. So that's because there are two separate systems. And what sort of repositories get crawled is another IT nightmare. So by collapsing those two layers, automatically any data that goes into Couchbase will also get indexed in the reverse index, which should be searchable. So if you build it that way, it's a lot more value. So you don't have to go searching for another search solution and integrate that. So we will build it in such a fashion eventually. First, we have to get a lot of stuff right about the database itself. So let me talk a little bit about what are we thinking. So whenever we think of roadmap, what we're building, we of course have to do incremental feature development, but at the same time, we're always looking for what are the foundational innovations we will make, or as Google calls it, what are the 10x principle, what are the 10x improvements that we can actually make. Those are the critical innovations. That's what excites us to be here. If I look, what are those foundational innovations we'll make? N1QL, we call it nickel. That comes from the database world of normal forms. The non-first normal form database is what we are. And so nickel comes from the query language for non-first normal form. The relational guys came from the academia, where there was a lot of theory and well-researched relational algebra based on which the language was developed, and there was an implementation to store the data for that algebra, which is what relational database management systems were. We base our stuff on generalized relational algebra, which relaxes the first normal form requirements. And what we have is a nested recursive model and a nested recursive algebra to describe that model. Just like the way relational algebra has a relational tuple algebra to describe the relational query language, we have the nested recursive model. What I mean by nested recursive model is a document having a subdocument which can have further subdocument within it. That gives you the nestedness, and we are able to query within that. Recursiveness is that important property which gives us the ability to go document within a document within a document by doing joins within them, kind of stuff. So that provides for a pretty rich and expressive query language. And what we have done is to do this in such a fashion that you don't have to go learn something new. This should be as familiar and equivalent to a existing SQL query language. So you should be able to do select start from. Instead of a table that you will give there, it will be a collection of documents or a key space or a bucket. That's where it will operate on. As you all know, query language is all very nice to look and program, but the efficiency of that is based on a secondary index that's going to back it. If you don't have a good indexing system in the back, you will do full table scans. That will screw your network, your performance, everything. So we're building a pretty cool secondary index in the back. And here we are also again changing the paradigm a bit. So far, in almost all database systems, indexes are co-located with the data, which all made sense when you're a shared disk architecture and stuff like that, but we are a shared nothing architecture where data can be across 100 nodes. And if you're going to co-locate indexes across these 100 nodes, then you go into this, what is known as scatter gather. You scatter across all these things, and you gather. That's how your final result comes in. So the performance and efficiency of your query now is at the mercy of how big your data spread is. If you have 500 node cluster, the scatter gather is across 500. Not the most efficient model. So what we have actually, what we're innovating on is the fact that we will keep these indexes. Let me give you a real life example. If you went to a library, these days libraries are a little too digitized. But in the classic day, if you went to a librarian and you asked them for a book, he or she will turn around, pull out a long drawer of index cards, look for something, and then give you, go for 849.2.37, which means a walk in that aisle, make a left, go to the last row, look in row number 2, you will find the book. Dewey Decimal System or whatever they would use. The index is central. It's behind this librarian. The data is located across all the 5 or 10 floors or however big the library is. If you put this index card right next to where the book is, The librarian has to walk across all these aisles, figure out where that book is, and say, oh, here's the index, oh, this must be the book. It seems a little counterintuitive. It wasn't, real life isn't designed that way. Somehow databases are. Which is what leads to this scatter gather, or like some of us call it, it's called spray and pray. Because your efficiency of your query depends directly on the weakest link. So the way we have developed the secondary index is that gives you independent, it becomes a cluster within a cluster. You can have a 500 node cluster of data, but you can vertically scale the index by having a different type of hardware on it, where you can actually put all indexes in just one box if you buy a big enough box. Or perhaps you want to put them only in 3 boxes. So the scatter gather happens only on these 3 boxes. It doesn't have to go across all these 50 boxes. So that is a fundamentally different architecture, where you are able to now not just scale horizontally, but also scale independent portions of the system differently as well. That control is, again, this is the second principle. First principle I talked about was layered consolidation. The second one we call late binding. This is the programming paradigm that we use here. We want to do as much stuff as possible at runtime in a dynamic fashion and not do it in design time static. Example is, like I was describing, our master node election. We don't designate a node to be master at the design time, it happens at runtime. I mean, having a schema-less architecture is another, which is a late binding thing, where you don't a priori define something to be a schema, and the moment you change it, you have to bring the system down, bring it back, and stuff like that. We don't do that. Similarly, the node, you can designate a certain node to be an index type node, and that will take on the properties of what the indexers need to do. Something, again, runtime. The dynamically tunable memory that we did, again, runtime dynamic, not a design time static thing. The bucket is live and functional. You just flip the switch. It's going to take a few milliseconds for it to warm back up. Otherwise, it's operational. You don't take the whole system down, no downtime, no maintenance. Nobody has to carry their pagers for the whole weekend for a system to rebuild. All those magic is taken care of. So the runtime dynamic nature, which we call late binding, we apply it consistently in whatever we're trying to build. That way, any price you're going to pay for doing something extra is only you get to choose how much price you need to pay. Unlike traditional database systems where you're paying the price every time for transactionality, whether you need it or not. So in our case, when we build those things, you'll be able to say, okay, persist this or replicate this or give me atomicity on this kind of stuff. You'll be able to do it on a per transaction basis, per operation basis. So that gives you that ability to not pay the price when you don't need it. So then the last thing we are on the server side we were innovating on, or we're discussing now, we have not actually put it in practice, is what is ACID for a distributed shared nothing architecture. What should ACID be? ACID being the atomicity, consistency, isolation, and durability that databases guarantee. This is what made the relational systems famous for. Even those professors who defined those systems now wonder whether we needed all those guarantees, because they defined all those things, and if you want to run the databases in that stringent mode, it's called serializability. The moment you put the database in that mode, it crawls, it doesn't even run. So nobody runs databases in that serializable mode. They always run it on a dirty read or a repeatable read or any of those lesser isolation level modes. So they themselves have existential question whether what we built, we did a pretty good job of selling it, but is it really solving the real life problem? So we really are taking a very close look at how we want to define ACID to be. Atomicity, what level of atomicity? We currently have a document level atomicity. That good enough? What happens if you have to do an update which affects 500 documents? Should it all happen, or that's what transactionality is? Should it all happen in one shot, or roll back all of them? Or is it okay to say that, oh, of the 500, 450 happen, these 50 failed. You, Mr. Application, go retry this. A lot of people are okay at doing that stuff. As long as you know the state of the system and you're able to describe it deterministically, perhaps there is in that continuum there is an answer. Storage tier, again, the 10x principle, we're innovating here, where the older database systems assume, like I said, strings and numbers, and they assumed the size and shape of the data to be concise. With the kind of data that we are playing with now, the blogs and tweets and other types of data, richer data, the size, there are no guarantees. And the indexing structures that were used earlier, B trees and B plus trees, they are less efficient for the new unstructured world. Forest DB is a fundamental differentiation in how it is done, because we have rethought how this index has to be. It is not a classic binary tree or a B plus tree. It's what is known as hierarchical B plus triad. I am no computer science expert there, but I know that each node is a triad. So that net result is that it collapses the height of the tree, which means that when you're looking for a certain piece of data, you're not going through the root node to the next node to the next. By the time you hit the leaf, it's a pretty deep scan. That is avoided by collapsing the tree height. That makes for two things. One is that the spread of the data is a lot less. In this case, it's concise. That helps with both storage efficiency, and because of that, performance is faster, because you're not looking across block boundaries and looking for data and stuff like that. A lot more data is compacted. We see a 10x differential in the kind of right, the classic word is, term is right amplification. We have 10x less right amplification than the others, and so correspondingly 10x better performance. If you go from a disk-based hierarchical like a B tree index to Forest DB running on a SSD, 10x retrieval speed is better in the case of Forest DB. SSDs are foundationally different from disks because their block I/O is very different from the way spindle disks work. And so we are working with a couple of professors to foundationally innovate in that area, where we want to take into account the parallelization that's possible within SSDs, as well as SSDs read and write and erase things in different sizes. Writes happen in pages and deletes happen in blocks, and the sizes are way bigger. One is much smaller, other is much bigger. So in place updates tend to cause a lot of problems in SSDs. So we're foundationally changing how we do disk IOs, and that will give us even more advantage in speed eventually. Our foundational architecture is what we call, as when we write stuff, it's called tail append architecture. We don't do in-place replaces. So that tail append architecture lends itself to SSDs, because you can do what is called as compaction, which is where you're actually trimming the data that you don't need in different block sizes than the way when you do reads or when you do writes. And the third area of innovation for us is mobile in Light. Light is our local database. We will use Forest DB there as well, so the speeds will improve, because in SSDs as well as in traditional hard disks, in Forest DB is 5 to 6x faster. So we want to see that improvement in both the server as well as on our Couchbase Lite product. Sync gateway will further innovate out there as well, not just taking care of deletes, but as well as the scalability of sync gateway. There's a lot to be done there, and we will sort of improve how many sync gateways can you run in a single node, and the bucket shadowing and stuff like that. We want to actually eliminate or reduce a lot of overheads that we carry right now. So those are foundational innovations there. And security is something I'm calling out here, but it's a constant theme both for server and the mobile product. because as more and more mission critical applications are deployed, security of the data, both when it is static and when it is on the wire, both are very important for our customers. And on the devices, it's even more important, because if a device gets lost, how secure is the data, or do you have poison pills, something that will wipe out the data and stuff like that. We'll build those sort of features so your local database is secure. You will anyway have the data on the server side, so how do we make sure that the local data is secure enough when it is static? And if for some reason you were to lose a device, how can you still have control over the fact that nobody else is going to get to your data? A very brief look I'm going to give you about sort of our proposed roadmap, and then I'll stop talking so you can ask your questions. And don't be shy. A lot of stuff out here, but generally 2014, a whole bunch of stuff we did. 2015, the main release is what we call as on the server side Sherlock, because we don't know yet what release number we should give it. We will let the product marketing folks duke it out with us eventually, but for now we gave it a code name. The most important thing out there is the nickel and the secondary index behind it. The third important piece out there is security, where the admin auditing as well as external authentication support with LDAP, other kind of stuff we are doing there. More data protection between our internode replication as well as for XTCR or cross cluster replication are the main things on the server side. On the mobile, we'll have better, more fine-grained queryability in our mobile database, along with encryption of the data that is stored in our mobile Couchbase Lite. Large attachments support. We do a decent job, but not as well as we would like to. And then we will have tooling for sync gateway and sync gateway administration and all that stuff. That's 2015. 2016, we will actually see few things like the SSD optimization stuff come in. ForestDB will become, ForestDB is currently being used in our secondary index. That's what we will see in 2015 release, and that will shake out a lot of bugs, hopefully. And then once we have that in place, we want to put it in the key value store as well. That's what we will see in 2016. Transactions, what is our answer to that, is the biggest thing that we'll produce in 2016. In a, like I said, for a NoSQL database with a shared nothing architecture, what is sort of asset would be the set of innovations that goes into that, the transaction processing and transaction manager piece. And on the flip side of that is the improvements on the developer productivity side of it, as in APIs that we will expose from the finer grained controls that we will expose through that. Both Nickel as well as our client SDK modules will be enhanced for that. On the mobile, pure JavaScript for offline is our goal at that point. So Cordova and whatever else, we have already done some innovation there, so we want to continue on that and give you JavaScript native offline experience. More advanced query capabilities, ForestDB integration on that side would be the. At the same time, we'll watch what people like Spread do and react to those the needs out there as well on the mobile world. Briefly leave you with what is it that we'll eventually get to building. Beyond the immediate, currently we of course are concentrated on getting the operational data store right. That's where all the transactions and the semantics of that and the secondary index and stuff like that. Eventually, I do want to provide a solution for the data lifecycle, one platform that can handle both sides. That doesn't mean that the same server has to do it. So somewhere where we can do real-time analytics, some historical data querying and manipulation, more like a data mart, definitely not a data warehouse. We will not get anywhere near that. We will leave it with a Hadoop confusion. So Couchbase server will maintain its pedigree of being an operational data store which is high performance and memory centric, which has got high availability characteristic with SQL-like queries and schemaless and powerful administration. Adjunct to that, we will have a Couchbase analytics server, which will be for historical data analysis, which will be more disk-centric, because historical data, you can't keep it all in memory and do it. Real-time analytics is slightly different, which we'll still try to accomplish. We can accomplish that with our view and view indexing capabilities on the Couchbase server. Historical analysis with a disk-based, disk-centric architecture. But the way things will come together as far as end users is concerned, there will be two interfaces which will be consistent. The way you manage it will be one way, which will be to use our existing administration framework, which is fairly robust. And the way you program to will be consistent because it will extend the nickel query capability, which will all be delivered through our client SDKs, but the nickel programming paradigm, which will be extended for these analytical capabilities as well. That's the long-term goal. Opportunistically, we will do the right thing out there, but at some point in the future, you will have a system where the data lifecycle I described can be handled in one platform, which will be the Couchbase server. So that's the real future look of where we want to be. So I've said a lot. Now it's time for you guys to say something. Questions? I'm happy to answer anything. It could be as silly as, why is this bug not fixed yet? To anything that you heard here but it's not clear. I mean, that's the whole idea of a meetup. Don't be silent.
There's no Couchbase mobile for iOS 8.
Why is there no Couchbase mobile for iOS 8? We will get there in short order. No excuse. Yes, that's something guys are thinking. I don't have a specific date to give you, but it should be short order, sometime this year. Anything else from anybody? No? I must have done a really poor job. Anyway, catch me. Yeah, please.
Just a question about RSTP.
Yes.
The description, something like understood, like fractal indices.
Fractal indexes?
Something like that?
No, it's not fractal indices. That's an entirely different world. What this is that it's called hierarchical B plus triad. Yeah. So what happens in this case is that each node in a B tree is a triad of three things. And that helps us to, and that triad, the way it is built, allows us to, how do I say, at the end of the day, like I was saying, it reduces the tree height by you building the next level of that only if you can find some stuff here. So otherwise in a B plus tree, what happens is that you keep adding to the tree, to the node, the moment you have. Here you can add more stuff at the first level. You can have a lot more values right there instead of it becoming deeper and deeper. That's what this thing, it kind of flattens the tree by giving you that triad allows you to add more at that level instead of you actually having, you can get to your values way faster instead of having like n number of hops before you can get to your leaf. It shortens that because of this triad. That's the foundation.
I'm asking that because fractal indices more or less you can control in some way the age of the tree.
Yes.
So you can get more and more advantage when you use in-memory and SSD.
Correct.
I think they are connected.
True. So same thing you can do with like LSM kind of things as well, where you keep some in memory and then you flush some to disk. We would try to keep more in memory and less on disk. And on any of these things, what happens is how efficiently you keep your disk structures and how less of a merge you have to do. Those become the issues out here. Here, the triads gives us the ability to do less of that. That's the advantage here. And by no means I'm an expert. You should look at this project is open sourced. There's a lot of literature on it. Feel free to read up on that. And
When I grow retired.
yes, true. Good. And if you build these things right, maybe it'll help you retire faster so you can make whatever your ambitions are faster. Good. Unless you have other questions, thank you very much for your patience.